for the weekend. Get that. Any questions at all before we get going? Things are going okay? Yeah. Well, let's see if we can finish up our exponential function. Oops, still muted. Our exponential function discussion, model of an exponential functions, I should say. Started talking about that last time, talked a little bit about doubling time and tripling time and all those good things. And then we started talking about how we can model with a general exponential function, or we write it in this form, where we have that a sub 0, e to the kt. What did the a sub 0 represent again? Yeah, that initial amount, right? Whatever is present at time 0. And then our main goal was to try to figure out what that k was in there, right? So we can get those functions. Okay, cool. All right. Let's do one more example where we've got a specific type of exponential function, and then we're going to talk about the idea of relative growth rate and play around a little bit more, and we'll be done with this section. So let's look at this next example. They give you a model here for inflation. You hear about inflation quite a bit in the news. So whenever you have an inflation rate quoted as a percent, you can figure out how much an item costs now will cost in a year, or will cost in 2 years, or how many ever years down the line using that formula. Let's just take a brief second and see why that's true. So if you said you had something that was $100 to start with, and you had 3% inflation, then in a year, the price would increase to what? 103, right? It's 100 plus the 100 times the 0.03, right? You would take the percentage times the amount, but then you have to add the amount on again, right? That's where the 103 comes from. Notice if I write it this way, I can pull the 100 off, and then I've got 1 plus 0.03 there, right? Notice the 100 here was the initial amount, and that 0.03 is the inflation rate. Right? Notice it's exactly what it has here inside those parentheses, doesn't it? The 1 plus the inflation rate, and then the initial amount here. Right? If you did it again for the next year, you would end up with what? Well, rather than writing it out with 103, for the next year, I would take your initial amount for the next year would be that, wouldn't it? Oops. That would be your initial amount for the next year. And then I would multiply that by 0.03 to figure out how much it increased. All right. Notice everything here still has, well, I can factor out 100 here, can't I? Still there. And I have the one, I'm just trying to show you where the formula comes from a little bit. You don't have to really worry about this part. I can factor out the 100 here. Oops, not 1,000, right? Now let's not do it that way. I'm doing a really bad job today. That's okay. All right. Let's treat that thing as a whole block. Notice I see this whole block and the exact same thing here. It's like factoring by grouping. If I factor out that whole block, I'm left with another, there's a 1 there and a 0.03 there, right? I get a 1 when I factor that part out and the 0.03 here. And now if I factor out the 100 out of there, I see the 1.03 and the 1 plus 0.03. And now I have 2 of them, don't I? Anyway, I was just trying to show you where the T came from. Okay. But I apologize for the confusion, but that's the idea where that formula comes from. Okay. All right, let's go back over to the problem then. So they give you the inflation rate is 2.5%. They tell you that you want to find what the new price of a motorcycle will be in 8 years. So what's the initial amount we're going to use? The 20,400. That's the price of the motorcycle now, right? So your motorcycle is 20,400, and your inflation rate in this case is what? 2.5%. To convert that to a decimal, it would be 0.025. So we'll have a 1.025 in the inside, and then raised to the t power. And so again, notice it fits our exponential model form, doesn't it? Like what we've had before. Okay. All right. So now, if we want to figure out what the price is going to be in 8 years, what do we need to do? Plug in 8 for t, right? Okay. So plug in your 8 for t. And what would you get when you put that in your calculator? 28,455, is that what you said? Oh, I missed the 4 and the 8. Sorry, flip-flopped it. And 42. Okay, cool. Thank you. Sorry about that. Okay. That okay? All right. So again, this just gives you another example of how exponential functions are used. If you've got something growing at a constant rate over a number of years, it's going to have an exponential growth idea. Okay. So like I said, these functions have applications in business as well as science. All right. One of the things that you'll notice when you go through Wettstein is they refer to something as the relative growth rate. It really is just talking about a particular constant. To get an idea of what it really means, you have to know a little bit about calculus, so I'm not going to go into a lot of detail into it. But when you've got your, when you've got your kind of general exponential model that we use with a natural exponential, okay, the relative growth rate is this number right here. It's that constant, it's that coefficient on the t. Okay. So that k is your relative growth rate. All right. When you think of, if you do anything with science, when you think of something as being a relative rate, you think about change divided by amount. So maybe you do a percent error kind of idea. So you do your observed minus true value and then divide by the true value gives you a relative error, right? Anytime you're talking about a relative rate, it wants to know change divided by total amount. The problem is that until you talk about calculus, it's a hard time talking about what I mean by change with this particular function. Okay. What turns out when you look at the change of this particular function, that number comes out. And when you divide it out, then you're just left with that number. You don't have to worry too much about that. Just know that this number up here is talking about change. The reason why that number up there talks about change is the bigger the number, the faster it'll change, right? Because if I think about putting a 2 in an exponent versus a 3 in the exponent, a thing with a 3 in the exponent is going to change a lot faster than something with a 2 in the exponent, right? Okay. So anyway, let's look at this first example, or this next example that we have in here. It says the population of the city in 2002 was 50,000, and in 2007 it was 56,000. The first thing it asks you to do is figure out what the relative growth rate is. Okay, so remember again, we're going to use that general natural exponential function to, pardon me, to model the situation that's going on here. Now notice they say in this particular example to let t equal to 0 correspond to the year 2000. So if we're going to let t equal to 0 correspond to the year 2000, notice neither of those populations they give you is your a sub 0, is it? Right? Now, however, what do I need to plug in for t to get out 50,000? What should go in for t to get out the 50,000 according to us then? What would you plug in for the t to get 50,000 out for your function? If you're going to let t equal to 0 correspond to 2,000. So plug in a 2, right? Because that's 2 years past 2,000, right? What should you plug in to get 56,000 out? So 7, right? Okay. So we have a couple of equations now, right? We know that our a of 2 should equal 50,000, and our a of 7 should equal 56,000, right? We agree? Okay. When we plug in 2, we'll get a sub 0 e to the 2k. When we plug in 7, we'll get a sub 0 e to the 7k. Make sense? Just plugging in the 2 and the 7? Okay. All right. It's asking us for the relative growth rate. So it's asking us to figure out what k has to be, right? Okay. Probably the easiest way to get at this is, I don't know what the a sub 0 is. I'd really like it to go away, right? I'd really like it to disappear. The easiest way to make it disappear would be to divide one by the other, because then they would just cancel out, wouldn't they? Okay, so if I take the a sub 0 e to the 7k and divide it by the a sub 0 e to the 2k, that has to be 56,000 over 50,000. And again, why am I dividing them? I'm trying to make that, I don't know what a sub 0 is yet, do I? No, I want to make it go away, don't I? Right? Okay. So I'm going to divide them so that the a sub 0 goes away. You can simplify the fraction on the left or the right-hand side. You get 56 over 50, which is what, 28 over 25, and you can convert it to a decimal if you'd like. We said the whole reason why we divided them is so that that goes away, right? Now I've got e to the 7k divided by e to the 2k. What do you do with your exponents when you divide? Subtract, right? So we'll get e to the what power? 5k. Now do we have something we can solve for k? What do we need to do to solve for k? Take the natural log, right? We want the k to get out of the exponent, right? And like I said, the big thing that I want you to remember with, the biggest thing that I want you to remember out of the entire chapter is, if you need to solve for a variable in the exponent, you want to take a log to get it out of the exponent, right? It's kind of the big thing I want you to remember. So take the natural log of both sides. what does what is the left-hand side now reduce to? Just a 5K, right? Remember, natural log and E are inverses of each other, so they just undo each other. We get the 5K. So now to finish this off, we would divide by 5. And be careful when you type these things in your calculator, right? That divide by 5 needs to be outside of your natural log, right? You could also write it as a 1/5 times the natural log if you'd rather. Doesn't really matter. And what value do we get? Two. Bless you. That okay? So that is your relative growth rate here when you find that K. All right. The second problem, or sorry, the second part is asking you to find what? Yeah, the population at the beginning, right? It's asking you to figure out what A sub 0 is, isn't it? That's what it's asking for, right? But now that we know what K is, we can go back and use either of the two original equations that we came up with to find it, right? Okay. So if we use the first one, if we use the 50,000, I can put in the K that's rounded. If you're doing these on your calculators, like keep the decimals in your calculator. Use your previous answer buttons. It's always helpful. What I need to do to solve for A sub 0 now. So in this case, my variable is not my exponent, right? But this is just going to be a number, isn't it? So I just need to divide it, don't I? Yeah. Just divide it over. So your A sub 0 will be 50,000 divided by E to that number. And you can do it in steps if you want to. You can compute this number in your calculator and then divide it over. Just try to keep as many decimal places in your calculator as you can so that you don't compound rounding errors from step to step. Anybody get a value for that? 752. As this is a population, I'll just round it to the nearest integer. What questions do you have on that one? That one okay? Are we happy with that? Is that not the number you got, Claire? Yeah, if you did you just points, yeah, if you typed in just the rounded, we'll make it rounding error, yeah. I would use your previous answer button or go up and grab the decimal and bring it down, either or. You should be able to use your arrow key to get it too. Okay. Yeah, the rounding, since if you round and since it's going in exponents, your rounding error will get really compounded if you round too early. Okay. Other questions on that one? This okay? Right. Let's see what else we got. Oh, says if the population continues to grow at the same rate, what will the population be in 2030? What would you need to do to figure that one out? Yeah, put in t equals 30, right? We just found, oops, I'll just write it this way. We just found that our function was 47,752 e to the 0.022t, right? We want to put 30 in for t. And solve. You get the value for that one? $95,203. Okay. We're going pretty quickly at that point. That okay? Any questions on that one? All right. So let's do a couple more examples. These last couple of examples on the on the last page here are doing some modifications of exponential functions. And so what I mean by that is we still have exponential functions that are pieces, but they're not written as that general exponential function that we have. So notice in this case, we've got a certain drug has been put in the bloodstream. It's asking you about, or sorry, it gives you a concentration in the bloodstream after a given amount of time. And then it asks what is the concentration after 20 minutes. So in this case, it literally just gives you the function, right? Okay. So what do we need to do to find the concentration after 20 minutes? See? Oh, plug in 20, right? Just put in 20 for t. Yeah? Okay. So your C of 20 will be 0.04 times 1 minus e to the negative 0.2 times 20. Put that in your calculator. And what do you get? So 0.039. I put okay. This one was a pretty straightforward one in the fact that it gave you a function, right? We didn't have to go hunt for a function. And it just asked you to figure out the concentration by putting in an amount. But I do want to spend a little bit of time analyzing this function and kind of give you an idea of why this particular type of function might be used to model certain things. Okay? Rather than worrying about this specific function, what if I wrote down, say, f of x equals e to the negative x plus a 1? Write it this way. Or, sorry, not e to the negative x. Negative e to the x plus 1, sorry. So notice I've written it kind of like what we had over here. I just didn't put a constant up in the top. Oh, I do want a negative up there. Sorry. I do want a negative in the top. I just put a regular x in there rather than a 0.02 times the x. Okay. Looking at this, and I asked you to graph this, because we've done these problems before, right? If I ask you to graph this, what would you think you would use for your base graph to start? E to the x, right? We agree? And remember that your e to the x graph goes which way? up and to the right, right? It has that horizontal asymptote down here, crosses the y-axis at 1 and goes up and to the right, right? Okay. Looking at my base graph and the function we're talking about, what transformations do you see? I got a couple of flips, don't I? Flip over the x-axis. And flip over the y-axis. I got both of them, right? Reflect about the x-axis. That's the negative on the outside. We reflect about the y-axis. That's the negative on the inside. What else do you see? Shift up 1. Good. Okay. All right. So reflecting about the x-axis would put you this way, right? That's a reflection about the x-axis. You agree with that? And then a reflection about the y-axis would make you go this way instead. Yeah. And then finally, I'm going to draw it on a new graph because that's the part that I care about. Finally, everything's going to get moved up 1, right? Agree? Okay. So, oops. Here at 1, your horizontal asymptote's also going to get moved up, right? And you're going to get a graph that looks like, okay? So this is the part that I cared about. As your function, or excuse me, as your x goes farther and farther out to the right, what does this get closer and closer to? The asymptote, and what value does it get closer and closer to? 1, right? So what this is doing is it's giving you kind of a long-term behavior idea, right? The farther you go out, the closer this gets to 1, right? So if I go back to the original problem, and this is why you use these types of models for certain situations, notice that I've got something similar here, don't I? What's inside the parentheses? That's going to get closer and closer to 1. We'll end up multiplying it by the 0.04. What this tells you is that your concentration of the drug in the bloodstream is never going to get above 0.04. It's going to get closer to that, but never get above that. Okay? So if you think about how this might apply, say, in medicine, maybe you've got an IV attached to a person and it's administering a drug every so often. Your body's going to filter it out because your body doesn't like foreign substances in it, right? So you need to figure out how much to put in there while your body's trying to filter it out to make it level off and have a certain amount of drug in your bloodstream to, say, kill off an infection, right? So you might want to model that concentration because you know how much should be in there to be helpful and not harmful, but you want to make sure you maintain it, right? So you can see why these types of functions might help you out to be able to figure out long-term behavior that you want to level off, right? I don't want the drug to increase forever. That'll kill you, right? Sometimes the treatment's worse than the disease, right? So I want it to level off. I need a certain amount of drug to kill things off, but I don't want too much of the drug in there, right? So I want to make sure it levels, right? And so that's why these types of models pop up in medicine as well. Okay? In particular, I could have done this a little bit simpler than going through all of the transformations. Let's look at just this piece right here. And in particular, all I really care about is the negative. We said the negative does that reflection about the y-axis, right? So if I just were to graph this piece, you would get something that looked like that, right? Going down to the right. And eventually, this piece goes to what? It gets closer and closer to what value? The farther you go out. 0, because it gets closer and closer to that horizontal asymptote, right? So let's see if we can use that knowledge to help us analyze what's going into the next problem, okay? In particular, as we look at the last part, okay? So in this case, they give you a different type of function. This one, we've got this exponential function, but it's in the denominator. They give you a number of people in a town that have caught the flu. That sounds familiar. All right. So it asks you how many people were ill initially, and then how many people caught the flu after 4 weeks. So that's the first two parts. To figure out how many people were ill initially, the initially is the key here. How are you going to figure out how many people were ill initially? What do you need to do? Let me ask it this way. How many weeks have passed if you're looking for when it happened initially? What week are you on? What week are you on if you're looking at the initial value? 0. So what do you think you need to do to figure out how many people were sick initially? Put 0 for T. Good. Exactly. Yep. So number of people ill initially will be putting in 0 for T. So I'll have 9,000 over 1 plus 999 e to the negative 0. Well, negative 0 is the same thing as 0. Anything to the 0 power is 1, right? So you'll get 9,000 over 1 plus 999. Well, 1 plus 999 is 1,000. So you'll get 9. So 9 people. It says round to the nearest person, but we don't need to round anything. 9 people. This is not a horrible idea to think about how to model something. A lot of times when epidemics break out, a small number of people come into the population and make a whole bunch of other people sick. We just did that like 5 years ago. Right? Yeah. That was a fun time for everybody. Great. Loved it. Better than cats. Okay. Anyway. All right. So in any event, this is a small number of people have come into the town. Okay. Now, does it make sense for this to go off forever, right? If I were to model this with an exponential function, does it make sense to model the growth by something that just goes off like that forever? If I have 5,000 people in the town, will 10,000 people get sick? No, right? It doesn't make any sense at all for that to go off forever, right? Somehow we've got to make this thing go fast for a while, but then somehow level off. Because you can't get, not everybody can, I'm sorry, you can't get more people sick than you have people in the population, right? Okay. So that's why we've got a different model, and I'll show you what a graph of this model looks like here after we're done doing the problem, okay? Are we okay with the first part, though? Okay. Second part, how many people have caught the flu after 4 weeks? What do we need to do for that?
Plug in.
Just plug in 4. Good. So you'll do n of 4. And it says round to the nearest person. Anybody get that one? 466. That was a pretty quick growth, right? 4 weeks later, 466 people are sick rather than just the 9. That also sounds pretty familiar. All right. That okay? All right. So let's talk about this last part and then talk about why, what the graph looks like and why it might look like something I drew over here. All right, so it says as t goes to infinity, so remember that's our notation for end behavior, right? We talked about end behavior back when we did polynomial stuff and when we did rational function stuff. We said that as your input gets big, either in the positive direction or in the negative direction, right? This is what happens as t gets big in the positive direction, right? Okay. All right, so let's look at our function. I'm going to write the function back down just so I can refer to it. And we're going to analyze it piece by piece. Oops. All right, so the first piece I'm going to analyze is this one. Okay. E to the negative t. Let's analyze that part first, okay? And I'm going to analyze it from a graph. Just worry about the graph of the thing that I circled in red, okay? We talked about it a second ago, or a minute ago as well. What does that graph look like? If I do e to the negative t, does it go up and to the right or down and to the right, since I'm doing a negative in the exponent? It's going to down to the right, right? Because it's going to flip it, correct? So it's going to go this way, right? Roughly, okay? So as t gets really, really big, as your input gets really, really big in the positive direction, what does your output go to? What are these values here on the right getting closer and closer to? 0, right? So this thing that I circled in red goes to 0 as t gets big. Well, if that piece is going to go to 0, what does your 999 times e to the negative t do? What happens when you multiply something by 0? It becomes 0, right? If that piece is really, really close to 0 and you add 1 to it, what's it really, really close to? 1, right? And if I divide 9,000 by 1, what do I get? 9,000, right? So as your t goes to infinity, your output goes to 9,000. Okay? So let me just go through the steps again, and then we'll verify this with a graph. Okay? We'll go graph this thing and verify it. Let's just go through the steps of what I did before, right? What did I analyze first? E to the negative t, right? I just looked at that part here with this function and said as t gets really, really big, it gets really, 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 really small. It might as well be 0, right? Go out far enough, it's 0, essentially, right? If I do 0 times something, I get 0, right? Add 1 to it, I get 1, right? So just work my way across, right? Kind of right to left there, didn't I? 0 times that is still 0, add 1, I get 1, and then divide it. That's where the 9,000 comes. That make sense? Okay. Nothing special about those numbers, by the way. If you would have had something that looked like, maybe I said f of x equals 50 over 2 plus 5e to the negative t. Let's see if we can figure this one out. Again, this part's going to go to 0, right? This will still go to 0, right? Which means this whole chunk will go to 0, and then you add 2. So what's it going to get close to? 25. Good, yeah, exactly. So this will be 50 over 2, right? So you'll get 25. As I should write an arrow. This will go to 25 as x goes to infinity. Okay. Right? We're doing something that's actually referred to as analysis, right? We're just picking out the piece of the function and trying to figure out what's going on. Okay. All right. I told you I would graph that first function. Let me go do that real quick so you can see that it really does get close to in 9,000. So let me go to Desmos here. All right, so the function again was 9,000 divided by 1 plus e. Oops. sorry, not 1 plus e, 999 e to the negative, I'll use an x. A sneeze, I think, but that's okay. Hopefully I'll hold it in here. Let me change my y value here to 9,000. And I zoom out a little bit. Do you see it getting close to that 9,000 value as it goes out? Right? Here's 8,000, 10,000 is up at the top. I'm halfway between. It really does get closer and closer to this, right? This is a relatively good model to use for things like epidemics, diseases, those kinds of things. Because what happens early? It goes up really fast early, right? And then what happens? Well, it runs out of people to infect after a while. Either you have it and you become immune to it, or you caught it and you died. One way or the other, you're not going to get it again, right? Okay? So one way or the other, you're not going to get it. So if you run out of people to infect, and the most that you could possibly get infected is how many people were there. So it's going to have to level off at some point. Okay. You might tweak this a little bit to get different models, but this is kind of a basic idea, right? Another thing that this is used to model is population kind of dynamics. If you say you introduce a species on an island, it's going to grow really fast early because it's got lots of room to roam, right? But if it's on an island, eventually it's going to run out of room. So it can't keep growing forever, right? It's going to have to level off at some point. This type of curve actually has a special name. It's called a logistic curve. Logistic, logistic curve. Okay. Just to give you a name for it. And again, these have lots of applications for lots of different modeling situations. Any questions on any of the stuff with the modeling with exponential functions? Feeling pretty good about it? Yeah. All right, we'll knock off a few minutes early here. Next week, we're going to get into a new topic called systems and linear equations. Hope is teaching on Monday. Yeah. So anyway, have a good weekend. We'll see you on Monday.